Okay, this is Math 8, Unit 5, Lesson 19, estimating a hemisphere. And if you know some words in here, we have the word sphere, and a sphere is like a ball, right? It's round, it's three-dimensional. And a hemisphere is half of a sphere, so it's cutting it in half like so. So it becomes just the round part, half of a sphere, is what a hemisphere is. And so today we're going to be estimating a hemisphere and how to figure that out using some figures that we do know. We've been playing along so far with things like cones and cylinders, and we know that a cone with the same radius as the base of a cylinder and the same height can actually fit inside of that cylinder. And the difference in volume between these two things is 1/3, meaning that this can fit, I could basically get 3 of these in there to fit in there. If I was to fill this with water or something, I could fill this up 3 times in order to fill that up completely. So this cone is 1/3 the size of this, or this is 3 times the volume of that one. Again, talking about volume, really, sorry. And so there's some things that we notice, we wonder, maybe we talked about this here. We know we could put them in there. We kind of wonder, if you took this with the same base, you probably could slide it right inside of there and it would fit, and then you'd have a little cone right inside there like that, and that would work out just fine. So anyways, things we talked about in class today, perhaps. So the next part, we're going to move into putting a hemisphere inside of a box, okay? And again, this is this dome shape, half of a sphere that we're talking about there. And we see in the picture that we have a radius of r, and this is important to think about in future lessons today or activities today, that if a hemisphere has a radius of r, that means it also has a height of r, because that's going to be the radius from the center part of the circle, right? The way a radius works, the center part of the circle is the same distance all the way around. And if you turn this into a three-dimensional object like a ball, and you get a center point inside the ball, it's the same distance to every edge of that ball. So whatever the radius is, that becomes automatically your height for that hemisphere, so to speak. We wouldn't call it a height because it's still dealing with a circular object, but to help you kind of keep thinking about things, there is a height element that is that same radius. So May has a dome paperweight that she can use as a magnifier. Here's your dome paperweight. The paperweight is shaped like a hemisphere made of solid glass, so she wants to design a box to keep it in so it won't get broken. Her paperweight has a radius of 3 centimeters. So we know that it has a radius here of 3 centimeters, okay, which means that it also needs to be at least 3 centimeters tall. What should the dimensions of the inside of the box be as small as possible? Okay, we want just to barely fit in there. So if the distance from here to here is 3, and that's half the hemisphere, I'm going to need to continue this around this way to get the full length of this box. So the full length is going to be equal to 6, right? It's 3 plus 3. Now in terms of the distance across this way, because it's a circle and it's a radius, I have 3 there and 3 there as well. So I know that the base of this box is going to be a square that is 6 by 6 inches, or 6 by 6 centimeters, sorry. All right, that's the base. In terms of the height of this box, the height only needs to be the height of the radius. We're only going up 1 of those. It's not going to double it up, it's only going up 1, which would mean the height would actually be 3. Okay, and the reason for that again is that's just the radius, that's the height of the hemisphere. So it needs to go from the bottom of it to the top of it, so we'd want to make it 3 centimeters tall. So our dimensions for this box are going to be a 6 by 6 by 3 centimeter box. For the volume of a rectangular prism is found by multiplying those together. So 6 times 6 times 3, which is going to equal 108, right? This becomes 12 times 3, which is 108, and we would say that's centimeters cubed. So what is a reasonable estimate for the volume of the paperweight? And this is where, again, we're estimating today. What would be a good estimate for the volume of paperweight? Because it's fitting inside of there, we know that it should be for sure less than 108 centimeters cubed. It should be less than that for sure. Right? What would that be? That's what you have to kind of think about. What could that be? Looking at the picture here, I'm going to look at it and say, well, you know what? It takes up a lot of space, but we definitely have all these spaces kind of around the corners that aren't being utilized completely. So maybe as an estimate, and again, this is just estimate, this is not a formula, okay? So maybe we could say that it's about 3/4 of the volume of the sorry, the box. Maybe. Okay, just an estimate, 3/4. That's just me thinking, we're kind of losing a couple space in the corner. Let's call it 3/4. So 3/4 of 108 would be something like 81 centimeters cubed. Okay, is that accurate? I don't know. I don't know if that is or not. I don't have the accurate formula. We're just playing with stuff for now to see, what do you think? What do you think? Okay, so maybe about 3/4 of that. Just an idea. That's just me thinking, I'm going to take off about 1/4, and so it's going to have 1/4 of kind of air space around those corners there. All right, that's just a way of thinking about it. You could have thought of something different for an estimate. Just, think it through. Why would you think that? In the second one, it says Tyler has a different box with side links that are twice as long as the sides of May's. Okay, Tyler's box is just large enough to hold a different glass paperweight. Now notice his side links are twice as long. So what's the volume of the new box? The old box was a 6 by 6 by 3, and since everything's twice as long, the new box will be a 12 by 12 by 6, doubling everything there, right? Twice as long. 12 by 12 times 6 is going to be equal to 864 centimeters cubed. All right. So what is a reasonable estimate for the volume of the glass paperweight? Well, so if he has another glass paperweight inside of his box too, right, how that draws out there, if he has one inside of here too, what is a reasonable estimate for that paperweight there? Well, we know it should be less than 864 centimeters cubed. If I did my same logic as last time, I would say maybe 3/4 of 864, okay? And so 3/4 of 864, when I do the math there, comes out to be 648 centimeters cubed. Again, this is just an estimate, and me still using 3/4 as a number. Just a number I picked because it kind of looked like it fit the picture pretty well. All right? How many times bigger do you think the volume of the paperweight in this box is than the volume of May's paperweight? All right, so how much larger is May's paperweight compared to, or what's the difference between that one and Tyler's? So here's May's, and here's Tyler's. And so May's we said was about 81, and Tyler we said was 648. All right, so how much larger is that going to be? Now, if I did the numbers on that, I might kind of figure out what that could be. But what we know is this. We know that we've taken this here, and if we had X was our initial, right? And we had that to be at a height, volume of 108 for the first box. And then we doubled all the side lengths. We multiplied everything by 2. We ended up with 864. So when I doubled over here, when I increased everything by 2, what am I doing to go from 108 to 864? Well, if I did a quick little math problem at 864 divided by 108, I come up with 8. So we recognize that this is actually 8 times larger, going from the first hemisphere, or first box size, to the second box size. So one box, the second box here, is 8 times larger. All we did was double the side lengths, but now it's 8 times larger than what the original was. Again, this is like saying I had a side length of A times a side length of B times a side length of C for that volume. And we doubled them all. So we had 2 times 2 times 2. So these 2's become 2 times 2 is 4, and 4 times 2 is 8. So I end up with 8 ABC. So the volume ends up being 8 times larger than what the original was when it was just A, B, and C. Okay, does that make sense? When I double each length and combine those doublings, I end up with an 8 there. So what does that tell us? Well, then when we're doubling the sizes here, we're going to do something exponentially with this as well. Why exponentially? Because this is 2 to the first power times 2 to the first power times 2 to the first power, which is 2 to the third power. And that's how you get 8. 2 times 2 times 2 is 8. So whatever I do, if I double something, my double is the times 2. Whatever I do, double it, I'm going to then take that to the third power. Okay, we'll come back to that later on as well, I'm sure. All right, let's move on over here. Estimating hemispheres. Again, a hemisphere with a radius of 5 fits snugly into a cylinder the same radius and height. Again, that's our height thing, right? It's 5, it's 5, it's 5 up here. 5 is our height because that's the radius. Calculate the volume of the cylinder. Okay, the cylinder is going to be volume equals pi r squared h. This will be pi times 5 squared times 5. So really we have 5 to the third. So 25 times 5 is equal to 125 pi is the volume of the cylinder. That's the cylinder's volume. So what do we think the volume of the hemisphere is going to be? Now again, looking in here, it's different than a box. The box I thought was like 3/4 of it, right? When I did the box, the cube, I thought, let's go with 3/4 of the size. This one seems to be filling up a little bit more, right? It just seems to be, there's less space in there. So I know when I think about it, in this case here, I know that if this is 125 pi, I know that a cone, and we'll talk about cones in a bit, I know, but I know that a cone also fits inside of there, and a cone is about 1/3, right? Well, the hemisphere is larger than a cone, so it needs to be greater than 1/3. So let's just say that it was maybe 2/3 of the cylinder. Okay, and this is an estimate, right? So if I said 2/3 of the cylinder as my estimate, then I would do something like 2/3 of means times, so of, the cylinder was 125 pi, right? So 2/3 of 125 pi, 125 times 2 is 250 divided by 3. That comes out to about 83 pi. That's my estimate for the hemisphere that fit in there, thinking that maybe it's about 2/3 the size of that cylinder, okay? Now look what happens in the next one. In the next one, we're going to take that same hemisphere, and now we're going to put it with a cone, which we know is smaller, but now the cone fits inside of that. So the volume of the cone is what we want to find out first of all. That would be 1/3 pi r squared h. Again, this is 1/3 of pi times 25 times 5. So that's the 125, but now it's 125 over 3 pi. And when I actually kind of did this part right there, just as a decimal to get a number, I come up with something like 41.7 pi. That's the volume for the cone, right? That's the cone part. So estimate the volume of the hemisphere. Well, the hemisphere looks to be a little bit larger than that, right? So I would say, when I look here, it's bigger than, so it's going to be greater than 41.7 pi, that's for sure, but less than the cylinder, which was, what was the cylinder one? 392.5? We didn't do that one there. If I multiply this out, by the way, this comes out to be 392.5 if I did the pi value there, right? So, is that right? No, something's wrong. Something's not quite right there. Let me think. Looking real quick. Yeah. So we can say less than the pi value. We're doing in pi. So let's just keep the pi stuff. So we said that was 125 pi. Okay, leave it in terms of pi. Sorry. So it's going to be greater than 41.7 pi, but less than 125 pi. That's the idea. So maybe if we take this, so maybe double the cone. And if we double the cone, 41.7 times 2, we end up with 83.3 pi. Okay? Again, that's just an estimate. We're just estimating what it could be. So if I'm doubling the cone, I'm going to be 83.3. So when I compare my estimates, though, the estimate on my first one, when it was inside of the cylinder, our estimate was about 83, right? And my estimate for inside the cone is also about 83.3 pi, right? So just comparing those things there, my estimates seem to be about the same. It doesn't mean that it's right. It's just an estimate, okay? And because I used the cone as something similar to start with and did a 3/4 and then 2/3, it probably is why I got what I got. But again, this is just estimating stuff. We're going to look at the way to do it properly tomorrow, okay, or in the next lesson. So in summary, we can estimate the volume of a hemisphere by comparing it to the other shapes for which we know the volume. So we can always estimate it based upon something we do know. You can find the volume of a cylinder and pick something inside of it. It'll help you figure that out. One part of this summary I really want to point out to you, because it's going to help you with your homework, one of your homework problems, is they do like this. They go through your summary and they talk about what we just did. Putting a hemisphere inside of a cylinder can help you figure out at least the kind of the upper boundary, the upper size of what that volume is going to be. Right? The cylinder here happens to be 3.14, so we know that's on our big side, 3.14. If I take that same cone and put a same hemisphere and put a cone inside of it, I can get a volume size of the cone as 1.05. Okay, which means that my hemisphere has to be somewhere in between that and that, right? Because it fits inside of this one, but it's greater than that one. So if I did like inequalities like this, it would look something like this. 3.14 is going to be, oops, sorry, the wrong way. 3.14, my hemisphere is going to be less than 3.14, but it'll be greater than 1.05. Does that make sense? So we have our hemisphere, that's our volume of the cylinder, is going to be greater than the volume of the hemisphere, which we don't know yet, that'll be greater than the volume of the cone, 1.05. This is the value we don't know. And so I share that to look at this last step here, which does come up in your homework as number 3C, that says averaging the volumes of the cylinder and the cone, we can estimate the volume of the hemisphere to be about 2.10 units. So they give a value here of 2.10. How'd they get that? They take the value of the cylinder and the cone and add them together and then divide by 2 to find the average. Okay? And that's how they get a 2.10. So if the hemisphere is 2.10, then they say by doubling that, that will tell you the sphere, which is 4.20. All right, again, this is just a way of estimating that. This comes up, like I said, in number 3C, so make sure you kind of pay attention to that one. Let's do your homework and pause the video, and then we'll come back and check it together. All right, on your homework. It says that a baseball fits snugly inside a transparent display cube. The length of the edge of a cube is 2.9 inches. So what do we have here? We have a cube like so, right? Little glass or plastic display cube, and inside of that cube is a baseball. Okay? Now the baseball is going to be inside of it, so it takes up some space there, but it fits in there just snugly, meaning there's not a lot of extra space. So the question says, is the baseball's volume greater than, less than, or equal to 2.9 cubic yards? How do we know? Well, the length of each one is 2.9. So to find the volume of the cube, I would do 2.9 times 2.9 times 2.9, which is the same as 2.9 cubed. That's the volume of the cube. Now, since the baseball fits inside the cube, it must be less than 2.9 cubic centimeters cubed. Has to be less than that. Why does it have to be less than that? Because it fits inside of that. That's the maximum volume in that cube, so the ball needs to be smaller than that to fit inside of it. So we'd go with less than. Number 2, there are many possible cones with height of 18 meters. So we have a cone, we have a height of 18 meters, all right, 18 meters. Let R represent the radius in meters and be the volume. Write an equation. Okay, sure. So volume equals 1/3 pi r squared times the height. Keep on going here. Volume equals 1/3 pi r squared. Our height is 18. 18 times 1/3 is 6. So volume equals 6 pi r squared. So that's an equation that represents the volume as a function of radius. We're going to use this now with this table right there. So complete this table for the function. giving 3 possible examples. So if the radius is 2, then we're going to have 6 pi 2 squared. 2 squared is 4, so we have 6 pi times 4, which equals 24 pi. No problem. Let's go ahead and double this real quick. So let's make that 4. So now we'll do 6 pi times 4 squared. 4 squared is going to be 6 pi times 16, and that's going to equal 16 times 6 is 96 pi. So we can already see when I doubled this, when it went times 2, this grew a whole lot more than times 2, didn't it? Okay, let's do another one. Let's double it again just for fun. Let's do a radius of 8. So I do 6 pi 8 squared, which is 6 pi times 64, and that's going to equal 384 pi. Alright, so if you double the radius of a cone, does the volume double? No, it does more. And explain how you know. Well, looking at it here, this is times 2. 24 times 2 would be 48. If you wanted to see how much it did grow by, we could do this. Let's do 96 divided by 24. And if you do 96 divided by 24, what you end up with is actually 4. So this is actually growing 4 times as much, right? That's a lot more, 4 times as much, which means, like we said before, we do the double means 2, and we square that value. And that gives us 4 times greater. Is the graph of this function a line? Explain how you know. Again, we would say no, and that's because it's not linear. Right? If we graph this out 2, and then 4, and then 8, 2, 4, 8, we have values that are here, here, and way up here. So it's going to be curving up that way, something along those lines. Okay, number 3. A hemisphere fits snugly inside a cylinder with a radius of 6 centimeters. A cone fits snugly inside the same hemisphere. Okay, let's remember that the radius is 6. The radius is 6 of this hemisphere. So if we have this hemisphere like something like this, right, and the radius is 6, that also means that the height of that object right there is also 6. So when it fits inside of a cylinder like this, that height is going to stay 6, and the cone is going to be here, which also has a height of 6. Really important that you caught that part there, because you might be going, where's the height? Remember, we said before in our lesson that that radius becomes the height of the hemisphere, but we still call it a radius because of just the shape that it is. So what's the volume of the cylinder? Cylinder volume equals pi times r squared times the height. So we know we have a pi, we know we have 6 squared, and we have the height of 6. So this becomes pi times 36 times 6, or in our case here, we'd have pi times 216, or 216 pi is the volume of the cylinder. So that's our cylinder is 216. For the cone, here's our cone part. The cone is going to be 1/3 of the volume of the cylinder. I don't need to read you the whole thing. So 216 divided by 3 is 72 pi, right? So we have the cone, we have the cylinder is 216, we have the cone is 72. So to estimate the volume of the hemisphere, we're going to find the average, just like we did in our summary. So we'll do 216 plus 72 and divide that by 2. So I take the volume of the cylinder plus the cone and divide by 2. That's going to give you 144, and then it's all pi. Okay? So that's the volume of the hemisphere based upon doing the estimates of those two things right there. All right, a couple more here. Find the hemisphere's diameter if the radius is 6. So we're looking for diameter, so we're going to double this, times 2. So 6 times 2 is 12. Finding the diameter, we have the radius, which is times 2. So 1,000 over 3 times 2 becomes 2,000 over 3. We have the diameter, find the radius, which is times 2. So 9.008 times 2 becomes 18.016. This time I have the radius, and I want to do the diameter, so I'm going to divide by 2 or multiply by a half, however you want to think about that. So 6 divided by 2 is 3. Here I have the radius, and I have a diameter. I'm going to multiply by a half because I have a fraction. So 1,000 times 3 times 1 over 2, right? This reduces down to 500 over 1, and I keep the 3 there, so I have 500 over 3. And then finally, this one here is 9.008, and I'm doing a half, so if I want to use decimals, I could multiply it by 0.5, right? That's a half. That would work out just fine. And you end up with 4.504, right? So I'm using a whole number, I'm using a fraction, using a decimal. It all works the same, right? So here's 0.5. That is the same as a half, 0.5. Okay, radius diameter. After almost running out of space on her phone, Elena checks with a couple of friends who have the same phone to see how many pictures they have on their phones and how much memory they take. Here are the results. This many photos, that much memory, that. Could the information be reasonably modeled with a linear function? Explain your reasoning. So for there to be a linear function, there really needs to be some sort of constant proportionality that's kind of reasonable, an approximation that's kind of close. We would find that by doing x, y, by doing y divided by x. Remember, recall that our constant proportionality is y divided by x. If I take this number and divide it by that number, I end up with something about 3.19. If I do this one divided by that, I end up with about 3.21, and this divided by that is again about 3.21. So I tend to have a pretty consistent number here for all these values, meaning that whatever y is, if I multiply it by about 3.2, if I take whatever the value x is, this number here, and I multiply it by 3.2, I can find the value of y. That's my constant proportionality, is what it seems to look like. So we could probably say, yes, we could draw a linear function, at least be really, really close to a straight line, wouldn't it? So if she needs to delete photos to create that much space, how many photos should she delete? Well, this is going the opposite way. If we're going to say I have 1,200, and I'm going to divide that by that constant 3.2, and when I do that, that gets me 375. That means if she deletes 375 pictures, she's going to free up that much memory space. And that's the idea. That's it for today's lesson, and we'll see you next time.